All right, well, welcome everyone. I'm trying a little bit of a new format here, so we'll see how it goes. No window here in my office, so maybe sunlight will not be as big of an issue with kind of the shadow on the page. We're approaching a time for a second exam, so what I have here is the sample version of exam number 2 for Chem 152. So we're looking at chapters on kinetics, equilibrium, and then equilibrium as it relates to acids and bases. So jumping in to problem number 1 here, we're given the half-life for radioactive decay of carbon-14 is 5,370 years. Part A, we're asked how long does it take for 90% of the sample to decay, right? And then part B, we kind of switch things around and we're given a time and we want to figure out how much of the sample is left. So hopefully you would see this problem and recognize that this relationship between the amount of sample that is left and time, and particularly half-life, is an integrated rate law problem. In this case, this is a radioactive decay is a first order integrated rate law. Generally, half-life is used to refer to first order reactions, although you can define half-life for a second order reaction. But any kind of radioactive decay is first order. It's just dependent on how much of the sample there is. Now, right at the back of the test, and this is saying this will be the same on our actual test, I'm going to give you all of the integrated rate laws, right? And there's also the relationship between the half-life and the rate constant here as well. So what's important for these questions is that you recognize how to use the equations, right? And maybe also which equation to pick, whether the reaction is first order or second order or zeroth order, which the best way to figure that out would be from the rate constant and the units associated with the rate constant. So in this case, this is a first order reaction for radioactive decay. There's two different versions here of the first order integrated rate law. One is giving us a ratio of our concentration at a certain time to our concentration at time 0, which is when the reaction started. So this first version of the equation is the best one to use for this problem, since problem number 1 here is dealing with percentages. If we're actually trying to solve for the concentration at a certain point, like concentration at time t, we might want to use the second version of the equation where the concentrations aren't present in the same ratio like they are here. But in this case, let me just transfer this equation over to our test because that's the one we're going to use. So natural log, I've got the concentration of the reactant at time t over the concentration of the reactant at time 0, and that is equal to negative kt. Okay, now let me bring that back into the frame here so we can see what I'm doing. For part A here, right, we've got the ratio. 90% will get us to the ratio. There's a little bit of a trick there. But we don't have K yet, but K is related to the half-life. So maybe that's something we should also do before we start thinking about plugging in here to solve for part A. Again, at the back of the test, half-life is 0.693 divided by K. Right, so if I rearrange that equation, I'm going to multiply both sides by K, divide both sides by half-life, the rate constant is 0.693 divided by the half-life. And since I have the half-life here, I can use that to solve for K. So 0.693, divide that by 5,370 years, and that will give me K. Now, that's all the formulas, at least for the moment. So let's jump back here where you can see the work that I'm doing. So plug this one into the calculator. 0.693 divided by 5,370 years. That will give us the rate constant here. K would be 1.29 times 10 to the minus 4th. And since we had years on the bottom there, the units would be per year here for our rate constant. So come back over to this formula. We've got K now, right? Now T is what we're solving for, time. How long does it take 90% of the sample to decay? The other trick here, if 90% of the sample decays, that would mean 10% is left. And what this ratio here represents is how much is left. Remember, it's concentration of the reactant at time t relative to the concentration of the reactant at time 0. That's how much stuff is left. So instead of the 90 here, we want 10% here. Now remember, a percent has 100 in it artificially. So let's change this to 0.10, which would be 10%. That's going to be equal to negative, right? And then KT, we just figured out K. 1.29 times 10 to the minus fourth per year, and the time here is what we would need to solve for. So that's going to be our missing variable. Now from there we can just solve this problem and figure out what t is. So I'll start over here on the left. If I take 0.1 and I do the natural log, that gives me, I'm going to move up here, minus 2.303 is equal to negative 1.29 times 10 to the minus fourth times t. Right? Now, because of the per year here, t is going to be in years, so I'm going to leave that out just because there's not a great deal of space here to do the calculation. Now, that's a little times, not a negative sign. So if I divide through by the constant here, that will leave t by itself on the right side of the equation. So I'll just take that minus 2.303, divide by 1.29 times 10 to the minus fourth. Right? The negatives are going to cancel out, and that's going to leave me with 17,849. Now it keeps going from there, but obviously we don't have that many significant figures equals t. Now, in fact, if you look at the problem, 90% here was kind of written as a one significant figure number. That's lazy writing by whatever clown wrote this test. So let's treat that as if it's two significant figures. If it was two significant figures, then we could keep 2 here for our time and call it 18,000 years. That's how long this sample of carbon-13 has been decaying. Now, if you had 3 significant figures, that might be a little better. You could say 17,800 years, right? But when you're doing radiocarbon dating, there's a pretty small amount of carbon that's left over if it's been a while. 1 to 2 significant figures is probably reasonable for what you have. I just don't want to round all the way to 1 because I forgot to put a decimal in there when I was writing the problem. Okay, so 18,000 years, that's our answer for part A. Part B is pretty similar. We're using the same equation, just we're given a different set of information. So we'll have to manipulate the equation a little bit differently. We're told in this case that the sample we're looking at, right, came from plant pigments, so carbon-based dyes, is 13,000 years old. And in this case, we want to solve for how much of the carbon-14 remains. Well, that again is what this ratio is in the equation. This is a ratio of how much is left to how much you started with. And we can easily turn that into a percentage. So I'm going to plug into this same equation. It's just we're going to be solving for this ratio now. So instead of concentration of R at time t over concentration of R at time 0, I'm just going to call it X for simplicity's sake. Still got that negative sign. Be careful of that negative sign. Times the constant, same constant here since we're looking at the same reaction, and it again is per year, which means our time should be in years. It is 13,000 years. That's going to cancel out. Now what we need to do now is solve for x. So let's multiply out the right side of the equation here first. And that gives me 1.677. So the natural log of x is equal to negative 1.677. What we need to do now is get rid of the natural log. Now the inverse of a natural log is e raised to the x power. So if I raise both sides, take both sides and raise e to that power on this side, that would give me x. On this side, I'd have e to the negative 1.677. That will be my value of x. So make sure that that's negative, raise e to that power, and that is your answer. And we really just have 2 sig figs back here from the 13,000. So this comes out to 0.1869, but if I round that to 2 sig figs, that would be 0.19. If I turn that into a percentage by multiplying by 100, right, so it asks for a percentage there in the problem, that would be 19% of the sample left. Again, if we had 3 significant figures like we have in K, if this was a 3 significant figure time, this could be 18.7%, right? But that doesn't really match the data we have. Okay, so integrated rate law problems, I would say certainly should be ready to handle something similar to what you see right here. We'll stop there and I'll come back for problem number 2 in the next video.